I'll say, okay, give me your points. Okay, so I'm going to do this really quickly. So it is 11:35 and 40 seconds. So here we go. This is a parabola that opens down. It hasn't been moved anywhere, stretched or shrunk, so it's going to have a vertex at the origin. We're going to go right one and down one, left one and down one. We're going to make a shape that looks like this. It would be impressive if you could label these other points right here. I'm going to label 0, 0 because that's an important one. I'm going to label 1, -1, and just to impress people, I'm going to do -2, -4, so they know, hey, I can not only stretch the easy points, I can do a tough one. This is a parabola. It's been moved to the right 3, so 1, 2, 3. Hasn't changed shape or anything like that, so it looks like this. I'm going to draw a really quick sketch. I'm going to do 3, 0. I'm going to do this one. This would be 4, 1, and I'm going to do this one would be that's going to be a +1, 4. Okay. Now, those aren't the only points that I could sketch and label if I wanted to. So on this one right here, this one's going to move to the left 1 and then down 2, left 1 and down 2. And then it hasn't changed shape, so I'm just going to go here and here. And then the same on the other side. So it's going to look like this. And then I'll label a couple of points. Always the vertex, -1, -2. I'll label 0, -1. And just for the fun of it, I'm going to do this one right here. This is 1, 2. I could label the ones on the other side if I needed to. This one is a parabola. It's been vertically stretched, hasn't moved anywhere, so the vertex is at 0, 0. Instead of going to the right one and up 1 squared, I'm going to go up twice as far. So if I do right 2, I'd normally go 4. I'm going to go 8. And then I'm going to do a mirror image of that on the other side right here. So it's going to look something like this. And as long as I label these points, I can convince people that I know exactly what I'm doing. Okay. This one is 1/3 the size. So it's going to look about like this. And I could label a couple of points there. And then this one right here has been flipped upside down, moved to the right and up 1. So right 2 and up 1, then flipped upside down so it looks something like that. I could really quickly get a decent sketch of that and have some points, 1, 0, 2, 1, and then 3, 0. I could have 3 points really quickly. Okay, that took 2 minutes and 30 seconds-ish, somewhere in that neighborhood. Okay, talking most of the time. You do not have to be that fast, but you want to notice that you're speeding up. I gave you about 5 minutes or so to work on this on your own. If you got done and you labeled a bunch of points and everything was good, great. If not, we just want to get faster. Emphasis on quick and accurate. Okay, take a look at the notes. We did a quick draw. I was looking through here. I'm going to make a couple tiny modifications to this. So the warm-up was the quick draw. We are analyzing functions. We are going to tear these functions apart so we know them inside out and backwards. Yesterday, we were talking about behavior on intervals. Today, we're going to focus on 2 things, and they're related. One of them is symmetry, and the other is what impact does absolute value have on when we do a graph. So when we're dealing with parabolas, they have some symmetry to them that makes them really nice and useful. And there are some other types of symmetry that can be useful also. So there are 2 types here of the symmetries. One of them is called even. The other one is called odd. So when we say they've got symmetry, even is just a way of talking about that symmetry. Even functions are symmetric with respect to the y-axis. And odd functions are symmetric with respect to the origin. Okay. Now, graphically is the easiest way to tell. So we're going to talk about that first. Okay. They are reflections across the y-axis. So what that means is if I go over here, x units, and up here, this point right here, xy, there is a mirror image of that across the y-axis. So instead of going to the right, I'd go to the left. So that would be -x, y. The y coordinate stays the same. The x coordinate is different. Algebraically, here's how we can check this. And I'm going to write this backwards. I'd like you to write the same thing. F of -x equals f of x. So, Mason, grab that door, would you please? Here's what this means. And this is why I like writing it this way. If you plug in a negative x, you get exactly the same thing as if you had plugged in a positive x, okay? So odd functions have symmetry with respect to the origin, and that looks different. If I go over here a certain number of points and then up, so I have this point x comma y, symmetry with the origin would rotate that 180 degrees around the origin, so it would be down here. So instead of going right, I go left. So this would be negative x. And instead of going up, I go down. So it would be negative x comma negative y. That's what these are right here. Okay, so those may be helpful, they may not. Looking at it is much easier to tell. We'll look at a couple of examples in just a second. I'm going to rewrite this one also. I'd like you to rewrite it as well. I'm just going to write this backwards, and here's what it means. If you plug in a negative x, you get out negative f of x. So this black writing that I just wrote, here's what it means. It means if you plug in negative x, you get the exact opposite of what you get when you plug in a positive x. Okay, and I'll show you a couple of examples of each one of these. It's not nearly as bad as it looks. So if you've got a graph, it is super easy to tell if you've got an even function or an odd function. So if we look at this right here, it's symmetric with the y-axis. You can draw a mirror line, a line of symmetry right down here. So this is an even function. It's symmetric with the y-axis, and we just want to grab a couple of points. So I'm going to grab this one, 3, 3. What's the point that's symmetric with that? Over here, negative 3, 3. Those are symmetric with the y-axis. So if I go to the right 3 units, I get a function value of 3. If I go to the left 3 units, I get a function value of 3. That makes it symmetric with the y-axis. That makes it an even function. If we take a look at this one, does this look like it's symmetric with the y-axis? Nope. But if I put a little dot right there and I took my paper and I spun it 180 degrees, this is symmetric with the origin, so this is an odd function. So let's grab a point right here. Let's grab this one. This is the point 2, 1. A symmetry point with that would be over here. It would be negative 2, negative 1. So if I go to the right 2, I get a function value of 1. If I go to the left 2, I get a function value of negative 1. Same number, just opposite sign. Okay? So it's symmetric with the origin. And this one right here, symmetric with the y-axis? Nope. Symmetric with the origin. Does it have rotational symmetry about the origin? Nope. So we're going to put neither right there, and then we're just going to say none. Absolute piece of cake to tell when you're looking at a graph. Everybody good there? Okay, so let's check algebraically. Here's how we check algebraically. Both tests start the same. This is why I rewrote the notes that way. So let's see what f of negative x is. 8, whoops, times negative x in parentheses cubed. Let's see. 3 x's and 3 negatives. 3 negatives make it negative, so this is negative 8x cubed. Now, make a comparison with the original one. This is f of negative x. How does it compare with the original one? Is it exactly the same? Or is it the exact opposite? Or is it neither? What's this one? It's the exact opposite. If it's the exact opposite, then that means it's going to be odd. Because here's what we were looking for. When you plug in a negative x, do you get the exact opposite or do you get the exact same? If you get the exact same thing, then we call it an even function. It's symmetric with the y-axis. If you get the exact opposite, then it's an odd function. It's symmetric with the origin. Okay, so this one is odd. F of negative x, plug in a negative x, and square it. So f of negative x turns out to be, let's see, 2 negatives. That's going to be a positive times the negative out front. Two x's, that's going to be x squared. So we're going to make a comparison between that and the original one. Is it exactly the same? Yes, it is. So guess what this is? Even. Okay, let's check this one. Change colors again. This is going to be f of negative x squared plus 2 times negative x. Always a good idea to plug in parentheses. We tend to make fewer mistakes with that. So f of negative x is, let's see, so that's just x squared, and that's negative 2x. Is it exactly the same? Nope. Is it the exact opposite? It's not. Now, everybody look up here. Okay, this one is going to be a neither. This one is a neither. Okay, if there's more than one term, you might have to do something like this. I'd say, well, maybe if I factored out a negative, that would make this negative x squared, and then that would make it plus 2x. Either way you look at it, these both have to have the same sign. One of them is negative, one of them is positive. Even if we factor out a negative or a positive, it doesn't make any difference. These are all going to be different signs. They're always going to be opposite signs. So they're not going to be exactly the same or exact opposite of what we started with. Everybody good there? That one's a neither. Would it display any type of symmetry? No symmetry whatsoever. Okay, now, can you take a guess why mathematicians called them odd and even? Lizzie?
Odd is like different, so it's different from the beginning.
Yeah, I'll take that. Odd's different. It's different from the beginning. Yep.
So would it be that if the x is to a power of an odd number, then it becomes an odd graph, and if it's to an even, then it's an even?
Yeah, but that only works if there's only one of them or some special cases and stuff like that. That might be why they called it that. It might have something to do with it, but don't rely on that. Now, this one says determine algebraically if these are odd or even. So let's take a look here. Careful with this. We're going to plug in a negative x. Now, this just requires some thought. Absolute value negative x plus 5. What's the absolute value of negative x? Yeah. Mm-hmm. Is it just plain old x? Okay, watch. Okay, what I'm going to need to do to make this work is I'm going to need to do this. If I did negative 1 in absolute value and then I put x over here, okay, I don't know what number this is. I need to guarantee that it's positive. So I need to have that left in absolute value. What's the absolute value of negative 1? Positive 1. So that's just a 1. This is absolute value of x plus 5. Compare that with the original. Is it exactly the same? Yes. So it is even. Let's take a look at this one. Again, I'm going to change colors. F of negative x. So this is going to be absolute. 2 times negative x minus 1. Absolute negative 2 times x minus 1. Okay, watch. Can I factor out a negative 1? Pull the negative out front. What's the absolute value of negative 1? 1. So I cross this off, and here's what I end up with. I end up with the absolute value of 2x plus 1. Compare it with that guy right there. Is it exactly the same? Nope. Is it the exact opposite? Nope. So guess what this one is? This one is a neither. Now, if you were to graph these, and you're welcome to use these as use a calculator on these, this would be an absolute value graph moved up. Is it still going to be symmetric with the y-axis? Yep. This one right here, and Jack's question earlier about, hey, doesn't this just move it 1 to the right? if you check, this does not just move it one to the right. Okay, there's some complicated stuff going on here. If you check this, and I urge you to check it, it's actually going to move it about a half a unit to the right, and it's going to be vertically stretched. Either way, if I move it to the right, is this going to be symmetric with the y-axis? Symmetric with the origin? Nope, so it's going to be neither. You're welcome to use your calculator to check something like that. Okay? Now, we got 10 minutes left. We're going to do some thinking on these, and I think we can make this work. Now that we've looked at what happens to a function, now we're going to take a look at what happens to a function when we take its absolute value. But what does it mean to take the absolute value of a function? So stop and think about that. What does it mean when we take the absolute value of a function? Absolute value refers to the blank from 0. Who can fill in that blank for us? Lizzie? Distance. It refers to the distance something is from 0. And distance is always positive. So listen very carefully. I think I mentioned this. When I was a kid, I was a complete nerd. Still am. Used to listen to a guy on the radio, and he said, the news always makes sense if you read it real slow. So if we put a function in absolute value, then no matter what we put in for x, the y we get out should always be, what do you think? Positive. So take a look at these shapes. These are regular old functions. But what part of this graph would have to change if I put in an absolute value? What part of these function values are not okay with absolute value? Wilson?
Everything under the y-axis.
Everything under the y-axis. So what would we have to do with everything underneath the y-axis? Flip it and make it positive. So we wouldn't get this shape anymore. We would get this shape. So our new graph would be kind of like a parabola, which, let me change colors, kind of like a parabola, then flipped up like this, and then the rest of the parabola like that. It gets pretty interesting on something like this. The part that's above the x-axis is okay, because we like positive answers coming out of absolute value. But if I were to put this function in absolute value, the part below the x-axis would have to get flipped up above the x-axis. So what used to be an asymptote at y equals -3 would have to be an asymptote at +3. So it would have to run along here, come down here, come to a point, and then it can flip back up. Now, what did we say was typical of absolute value graphs? Some sort of V shape. And there are V shape. We happen to have 2 V shapes here and 1 V shape here. So if you come down below, these are the actual functions, and you can make your calculator do this. In the math number menu, there's an ABS. You could make it graph this. This is what it would look like. Okay? Now let's analyze it. So the criteria we want to do is, hey, what's the domain? What's the range? What are the intercepts and all that sort of stuff? And they did us the favor of putting a graph here. So domain, is there any problem with putting any type of number we want in there? Nope. No square roots, no division, so -infinity to infinity. Because we took the absolute value, we don't get any negative values out. The lowest we get would be 0, and then we go all the way to positive infinity. Intercepts, x-intercept at -2, 0, +2, 0. Those are the x-intercepts. And the y-intercept is at 0, 4. Where is it increasing? I just shaded some areas on the x-axis. If you look above on the x-axis, is that where it's increasing? So this is going to be from -2 to 0, and then again from 2 to infinity. Best to do round. That means it must be decreasing everywhere else, so it's decreasing all the way over here and here. So that's going to be from -infinity to -2, and then again from, union, sorry about that, union 0 to 2. We doing okay? Where's it positive? Almost. Lizzie? Almost everywhere. Negative infinity to infinity, except 2 places. It just barely disqualifies itself from being positive because where?
When x equals 0.
When y equals 0, okay, which would be at plus and minus 2 at the 2 of those places, okay? Keely, is this graph ever negative? No way, because we put in an absolute value. We're always going to get positives, okay? So we could say never. Maximum, right there, 0, 4. Minimum, kind of a tie. Kind of a tie at negative 2, 0 and 2, 0. Both places they tie for the lowest function value. And then symmetry, what do you think? Odd or even? Caleb, what do you think? Odd or even? Even. Okay, so we're going to write even and we're going to write symmetric with the y-axis. That's the type of symmetry we're talking about here. And then end behavior, we're going to write the limit as x approaches negative infinity, and we're going to write the limit as x approaches positive infinity. Oops, I had to write f of x there. And then say what the limits are. Okay, we doing okay? Keely, as we go to the left, what happens to the function values? Up. Up toward what? Positive infinity. The x's go toward negative infinity, but the function values go up toward positive infinity. Okay? Andy, as x goes to positive infinity, so as we go up to the right end, what happens to the function values? They go to positive infinity. They both go up, which makes sense because they both better go to positive because we took the absolute value. Everybody good there? All right. Okay. Yeah.
Why is the maximum at 0, 4 and not infinity?
Ooh. Oh, listen to this. That's awesome. Okay. Did you read ahead or did you think of that on your own? Way to go. Very nice, Lizzie. Okay. So I have an asterisk by this one because I want you to think about this. Is the maximum value we found right there, is it really the maximum value for the function? No, it's not. What is the real maximum of the function? Okay, now, infinity is an idea, so this does not have an actual max. Okay, so 0, 4, write this down here. 0, 4 is what we call a relative max. It's the biggest one in a little neighborhood around there. There is no absolute max. There isn't an absolute max on this one. There is a minimum for sure. We hit a bottom, but we don't hit a maximum. Okay? Now, if you'll read that little note right there, what it says is this falls in a general category of things called extreme values of functions. Fancy word for these would be global or local extremes, global max, global min, or relative max, relative min, absolute max, absolute min, stuff like that. Okay? So, would you circle at the bottom of the page how you're feeling right now? We're not quite out of here yet. Bell's going to ring. Okay? I want to talk about one more quick thing before I let you go. Hold on one second.
Oh my God.
Okay. Given that graph, could you answer these questions?
Yeah.
You okay with this? Okay. Does this function have a minimum?
Yeah.
Yeah.
Yes. Technically, does it have a maximum? No, it doesn't, because there's no limit to how far up it goes. All good? Okay, let me just say one last thing. If you are having any struggles with any of this, we don't have a test on this until a week from tomorrow. Okay? So it's next Wednesday when we have a test on this. If you want some help on this, please come see me. I love talking about this stuff. Do finish this one up, or at least run through the details of it, and then get going on your homework. Have a great day.
So which one?
Go ahead and put down the relative, Max.
Again.
So we're increasing here from 1 to infinity. Decreasing here, negative infinity to 1. Positive everywhere, except for x equals 1. It's never negative. Minimum right here. Oops, max, none.
Are we hiring someone new? I saw Brian taking someone around the building, asking him like questions, like almost like an interview, like saying like, "Oh, so you've done that? Okay, well, let me show you this and that." I was like, wondering if there